So we'll wait for 2 minutes. So hi Taruni, hi Dinesh. So this is the fourth session on NPTEL, and so the third session was already recorded. That that was uploaded yesterday. So the Dinesh, the question you have asked regarding the energy balance, where the energy is going. So I have clarified in this recording also, but I would like to clarify again that basically when you are rotating fluid. So basically, there is always a energy that is going to the viscous dissipation, and that leads to the diffusion. But the thing is that the diffusion is so small. The energy given by us to the system is so small that we are unable to look into that diffusion. Uh, and when we rotate it back, there is again some very small diffusion, but most of the dominance is shown by the flow, that is due to the pressure difference created, and you will see the streamlines in one direction in a particular way, and then we rotate back, you will see we are basically changing the direction of the pressure gradient, and then uh, the streamlines are actually trying to reverse back the same lines. So in that case also there is a small diffusion, but that diffusion you are unable to see. So so the idea behind this is that there is a diffusion, though it's small. If you take something, uh, any system where you are having a Stokes law valid, and then you are also having a uh, greater diffusion, then you will also able to see diffusion, uh, great amount of diffusion there. But the thing is, like, where the energy is going, the question is that, and that was so I clarified that in the last recorded lecture, and here also I'm telling. Fine. Anything? So in the last lecture that was recorded, so that if I have derived the thermal time scale, then I did numerical on the thermal time scale. Then I explained the difference between the two frame of reference, that is Eulerian and Lagrangian, and then I have found out the relation between the Eulerian and Lagrangian derivation. And continuing to that, in today's, that is the fourth session on NPTEL, I will be taking the Lagrangian description and will deriving the Reynolds transport theorem again for you, because that is certainly a part that will be having doubts. And then I will be deriving the Cauchy momentum equation and Navier-Stokes equation if time uh, permits. Okay, so Tharuni, do you have any doubt till now, apart from all this discussion?
No, sir.
Okay, Dinesh, do you want to say something? I am unable to hear you, I think. I am unable to hear. So basically, it's a fourth session. Okay, fine. So basically, today we will be going to discuss multi-phase flow session 4, NPTEL, and my mail ID is this. For any doubts, you can always contact me. So basically, the agenda of today's discussion is I will be deriving Reynolds transport theorem, and I will be deriving uh, Cauchy's momentum equation, and uh, also I can derive Navier-Stokes equation. Basically, all these three derivation I will be going in Eulerian frame of reference. Sorry, Lagrangian frame of reference. Where I am tracking a material point or the fluid particle with time. So basically, to start with this, I just quickly go through the frame of references that I have discussed in the last session, in the recorded session. So in this session, what I've discussed is, so basically there are two frame of reference in the Eulerian frame of reference. It's called the fixed frame of reference, and the Lagrangian frame of reference. We are moving along the continuum point. So basically, if the fluid is flowing, you keep your eyes fixed at one position and you are looking at the flow. And then you are looking at how the flow is, whatever the velocity of the property is changing accordingly. But in case of Lagrangian, you are moving along the continuum point. So there is a flow, there is a fluid particle that are flowing with it. And basically, you are changing the position. You have fixed the fluid particle and then you are following that. So basically, if it is here at an instant, then after some time it goes here, then you are basically following this particular fluid particle. So in one case we fix our position, in another case we fix the fluid particle. Okay, and we are following that. So in when we are fixing this fixed frame of reference, the properties depends on the particular space and time. While in case of uh, Lagrangian approach, it depends on the particle that we have fixed or the initial position of the that fluid particle that we are following. The properties depends on that, and that's why we call this to be a material point or the continuum point, whatever. So basically, for an example, let's say if this is the particle at x, it has velocity v, and any particle, if you are tracking this particle, it also has same velocity v at this point. But it depends on this, and if it is coming from here, you are tracking this particle, but at this particular point, both have same velocity, and that's the way to relate the Lagrangian and the Eulerian references. So basically, if you look at, let's say we have some uh, volume that has changed to this in some time. So it is at now at a position x, This position is now dependent upon, if you want to relate, then this position is dependent upon the material uh, coordinate, that is zeta I am considering. So this is material coordinate. I am fixing this particle. So this position depends on this initial position of the particle. You can reverse it back. You can go back, and then you will see that if you fix yourself here and you are tracking x, then zeta is a function of x. So I hope it is clear. If you have having any doubt till now, then you can ask me. Anything else? Dinesh, Taruni?
No, sir.
Dinesh, do you have any comment in the chat? I think I'm waiting if you have any comments. Okay, fine. Okay. So basically, there are two derivatives. That is one at the fixed point, one that is obtained when you are fixing the point, another when you are fixing the material point. Okay. So this derivative is generally called as material derivative or the substantial derivative. And in case of Eulerian derivative, it's so simple, this derivative at a fixed point that we are calculating. But in material derivative, you will see how we relate this material derivative with the Eulerian derivative and why it is important. So I am taking a skydiver problem, that is a skydiver problem that is given in Lille, advanced transport phenomena. So here, if you see the diver, there is a diver that is coming down in z direction due to the gravity, and there is a temperature gradient. There is a linear temperature gradient in a particular direction, and there is a change from T0 to T1. And what you will see is that as you fix your position at a particular point, you will not see any change in the derivative. So it means that Eulerian derivative is zero in this case. But if you are going from here to here, you will see there is a change in the direction. So there is a change in the temperature with the direction. And so dt by dt comes out to be, from the inspection by itself, you can see that it is velocity of the diver and the multiply with the temperature gradient. So temperature gradient is this. Okay. So this is one of the problem to feel like how the Eulerian derivative uh, is calculated or how the material derivative is calculated. To relate that, we are assuming this example, and we are calculating the material derivative. So basically, this is nothing but the derivative of B with fixed zeta. That is, we are fixing the material point. And then zeta is dependent. So we want to relate this to the Euler derivative. And in order to do so, we are relating this zeta with x. And we know that when we are transforming coordinate from here to here, so from zeta to x, you will see this transformation, and then x is now a function of zeta and t. Let's assume that there are three coordinates, x1, x2, x3. And so when you when you apply chain rule for finding out the derivative of this function, you will see at constant zeta, you will get del b by del x1 by del t at particular zeta, and so on. And at particular, when x is constant, you will get del b by del t. So basically, what you will get is, this is the Eulerian derivative because it is at fixed point. All of these are material derivative that is coming from by fixing this. Okay. So from here, what we get is the substantial derivative should be equals to v dot grad b plus del b by del t. Okay. So this is the way we are relating the two frame of references. So we are going to use this to derive. Basically, I wanted to derive the Reynolds transport theorem, and we will be going to use this relation in further derivations. So if you have any doubt, anything, you can ask. If at all anything is not clear. Anything? Tarun? Dinesh?
No, sir.
Is it clear? Or is it,
Yes, sir.
are you unable to understand it?
Yes, sir.
Okay. So, okay. So, now I will be going to derive Reynolds transport theorem. And what Reynolds transport theorem says, it's basically we are going to find out the substantial derivative of a finite volume. So basically, we are having some finite volume, and we with time, how it is evolving, we need to find. And so let's say we are having uh, this material volume. Let's call it to be something B. The area is A and volume is T. Okay. Now at some time delta T, after some time delta T, there is a change, and in the change in this quantity, some quantity that I'm assuming B, in a particular material volume at Vt plus delta T, or I think I can. Okay. At V, so V becomes Vt plus delta T. Okay. And that is, uh, this translation occur because of the normal velocity of the material volume. So my agenda for this problem is to find the substantial derivative of this quantity B. Okay, or I can put V only. So I know how to write B dV, how to write this derivative. So in the limit, in a very small limit, that is delta T tends to 0, there is a change in the property of B, that is they are in a particular volume. With time, there is a change in that. I need to put a charger on it as well. So B is some quantity that is per unit volume. And so, so what we are getting, so in time delta T, we need to find this derivative and how it is changing. So it is basically goes from T plus delta T. That is the usual how we write that any derivative. dV minus, that is V T plus delta T, minus B T dV Vt. Okay. So now what I can do is I can rearrange it in a way that I will add and subtract some part of the property t plus delta t dv t plus delta t minus b at t plus delta t. What is the change in uh, b, but uh, within this volume? Okay, plus I have to subtract and add the same thing, t plus delta t dt vt minus b at t dv vt. Okay, so basically I'm just add and subtract this part in this usual form. And why I'm doing is I wanted to see that what is this part. Okay, so I'm able to write it like this: b t plus delta t dv v t plus delta t minus vt. V is the material volumes. For to understand this, the material volume. Okay, so this is this plus what we get here from here is b t plus delta t minus b of t dt, and 1 by delta t is there also, so I will take delta t inside. So that is my d by dt of b dv. So the change in volume from from t to t plus delta t uh, is basically the area that can be related as that can be related using the normal velocity. Okay, so Tharuni, any issues till now?
No, sir.
You can ask really, and you can also switch on your camera so that you can discuss. I will understand if you are able to understand it.
Actually, I'm good at with this part, sir. I'm facing trouble with assignment, sir.
Yeah, that's I asked before uh, deriving this, like what is the issue? Which assignment you are talking of?
Week 4, sir. I
Okay.
had gone through the derivations discussed in the video, but I couldn't find some formulas and related topics.
Uh, okay. So first I conclude it and then I will resolve your doubt, right? Just after
Yes, sir.
the Reynolds transport theorem. Is it fine?
Yes, sir, no problem.
Okay. So basically, you can relate this change in volume using So we know, I already tell whatever the change is happening in the volume from t to t plus delta t is because of the normal velocity. And so we know that how the change in volume is related with area and the velocity, that is v dot n, that is the normal velocity, into in time delta t and dA. Okay.
Yes, sir.
So basically you can rewrite it like this. The limit delta t tends to 0, 1 by delta t, this become v dot n delta t dA, and b will remain as it is, that is, so I should write b t plus delta t v dot n delta t dA plus this will become in the limit delta t limit tends to 0, this will become del b by del t, right, into dv. Okay. So if you take del t under, this will cancel out, and what we get is, you can go back again using the Gauss divergence theorem. You can take area to volume integral, and what we get is b v dot del, that will become del dot of bv into dv plus del v by del t into dv is at vt, and so what we get is d by dt of any quantity per unit volume, material derivative should come out to be del dot bv plus del b by del t to dv. Okay. So this is with respect to t. So this is called to be as Reynolds transport theorem. We are calculating the rate of change of a quantity per unit volume in time, and when we are tracking the material point. And so we found out this. Okay. So I hope it is clear regarding
Yes,
RTT, right?
sir. No problem, sir.
Okay. Now let me know the problem first. Like, what is the issue you are facing? In which question you are facing the issue?
I couldn't formulas exactly for some of the questions. Coming to the pressure flow calculations, we have stratified flow. In that,
Okay.
there are formulas for theta calculation.
Which question you are talking?
First question,
First question. Hello.
yes,
Which
yes,
question?
first
First
question.
or first?
Mm, First question in week 4.
Assignment 4, first question.
Yeah,
What is that? Can you read out for me?
yeah. Can you wait for a second?
Yeah.
Shall I read the question?
Yeah.
Here basically what they had given is a horizontal pipe of diameter and length was given. Water flow rate, gas flow rate were given with water
Okay.
fraction,
Okay.
air density, air viscosity, water viscosity, and laminar flow, turbulent flow. There was given equations. So
Okay.
the first is the interface is going on with water and air. We have to find the angle. So in the video, I found that in order to find the angle, theta minus sin theta by 2 pi. But whereas in Google search, I found out that tan theta is equals to Fg by Fi. By directly frictions, we can calculate.
Uh, 1 minute. I am unable to see the question. Uh, just wait a minute.
Yeah.
I'm just opening it.
Yeah, okay.
Week 4. Okay, so air, water flowing through a horizontal pipe of diameter 20 centimeter, okay, and length 200 meter. Water fraction, okay, 0.3. And you need to find the theta. Okay, so what's the doubt?
Mm, calculation of theta there was. In the lecture, they have provided relations for epsilon L and theta, like theta minus sin theta by 2 pi.
Actually, I'm not allowed to tell assignment questions before its deadline.
Okay. Can you discuss about Schiller-Newman correlations? I mean, for what relations we'll be using that in Reynolds number at which conditions?
What?
Mm, Schiller-Newman correlation. I mean, what signify and why would you use that?
Okay. Can you share your screen and let me know what you are really asking, because I am unable, because your voice is very big. Maybe I will give you some hint.
Actually, if you are opening on the assignment page, you can go back to question number 10.
Question number 10. 10 or 1?
Yeah, 10.
Okay, 10. Okay. Schiller-Newman correlation is applicable for. So what?
Actually, I'm asking what does a correlation signify? I mean, why it is used?
Why did we?
Why did we use? I mean, why we have to take that correlation into consideration like that?
Uh,
Actually, we have Stokes result, right? In there, we are considering Reynolds number. We have cyclic equations and many equations. What is the correlation signal I'm asking?
no, first question is that why we use Schiller-Newman correlation. Another question, what you are asking?
I mean, what does it signify and at which conditions we can use that?
Obviously not going to tell with conditions because that's the question.
Okay. Mm. I mean, what does it
Basically,
signify? Why we have to use that? Mm.
yeah, so Schiller-Newman correlation is basically used to model the drag force between the particle and the fluid.
Okay. Drag force and the fluid.
Yeah, drag force between the particle and the fluid.
Okay.
Anything, which you are asking any other question?
No, I'm not asking. I'm okay with that.
Okay. So why are you asking this question? Like,
Actually, in the lecture, I couldn't find that person's name.
okay,
Maybe I
okay,
got missed or I don't know. I'm searching for it like that.
okay, fine, fine.
Maybe
Any,
I can ask next week if I have any doubts.
yeah, and I also didn't go through all these assignments, but
If
yeah, I am
possible,
not allowed to
could
solve
you share?
what?
Yeah, that's okay. Anyway, I can ask in the next session. That's not a problem.
That's fine.
As for now, we have completed 3 assignments, right? Can you share that answers also, solving answers? That will be good for us to help.
No, actually, the thing is, like I am not that TA that who. There were other TAs who are submitting those who are making questions for that assignments and all. Uh,
Okay.
I am not the one who is doing all these things, but I can always, I am here to solve any doubt related to this lectures and the
Okay.
assignments that are already done and any
Okay.
questions related to that.
Yes. Uh, Coming to week one,
Okay. Yeah, I'm opening week one.
and yeah,
Yeah, which question?
fifth question.
Okay.
How can I solve it? I got the answer in the range of 2000s, but the accepted answer is in the range of thousands.
Okay. So it's easy question. So yeah, I'm going to tell you how we can solve it. 1 minute.
Yeah.
I think I have derived in the first lecture itself. I did that question. You were there in that first lecture?
No, actually, I didn't attend 3 sessions because of my college.
Okay.
Okay, if you have done, I'll go through previous lectures. Mm,
Uh, yeah,
in that
I derived
same
for the
week,
mixture density. There was a question on mixture density that I discussed.
yeah, Sixth question and seventh question on mixture density.
Yeah, I think mixture
Okay,
density.
I'll tell the questions. If you have done it, I'll go through the lectures. If not, you can explain me.
Uh,
Is that okay with you?
yeah. You can also. Yeah, I can tell you here also. That's not the issue. Just
Yeah. Can you go through the eighth question?
yeah, 1 minute. Yeah, in an oil water mixture of oil 50 ml and water is 150 ml, water density, oil density. This first phase mass concentration. So all these derivation were
Mm.
there in lecture, I guess, isn't it?
Lecture, I found it, but I'm not getting the formulas, how to solve it, how to use that. That's the problem there came. Actually, I got in the answer 170, but the concentration was in the range 0.28. I didn't get that.
Eight question. Yeah, 1 minute. Let me see the correct. I will see if I will be having. I will be able to show you the solutions. Otherwise, I will solve it for you.
Okay.
Just give me some time.
Yeah, okay.
There is a connection issue. Just give me a moment. NPTEL. Sheet. I just log in. Really, I am unable to log in that account. This one, yeah, now tell me. I think I will. Okay, which question you are telling? Now tell again. Assignment one. I think you are muted.
Yes, assignment 1.
Yeah, assignment one. Which question?
Just a second. Question number 8.
Question number 8. But you are unable to see the solution. To the like explanation to that.
No.
Okay, so maybe I'm not allowed to show that, but I am solving it for you.
Okay.
Okay. So the question is assignment. Okay, let's wrap up this. So I am not following this discussion more. I will discuss it after all the doubts, or maybe in the next session about RTT and Navier-Stokes equation. For now, I'm solving all of your doubts, like all the assignments, all the previous assignments. Fine, it's fine. Yeah. So in assignment one, you are having a doubt in question number 8.
Yeah.
Let me read out it. So in an oil water mixture, volume of oil is 50 ml and water is 150 ml. Water density 1000 kg per meter cube and oil density is 870 kg per meter cube. This is the question, right?
Yes.
Find out the dispersed phase mass concentration. We need to find out the dispersed phase mass concentration, right?
Yeah.
So we have volume of oil, that is 50 ml. Then we have volume of water, that is 150 ml, right? Then
Yes, yes.
we have density of oil, that is 810, right? And
Yeah.
then density of water, that is 1000 kg per meter cube. Okay. So we need to find the dispersed phase bulk density. So basically, we need to find, so mass of, which is defined as mass of oil. Dispersed phase is what? First, that you should be identified. I think you did a mistake here in understanding what will be the dispersed phase, right?
Yeah, maybe.
What do you think? What will be the dispersed phase? Oil or water?
Oil.
Yeah, correct. Then what? Uh, then it is just this only. So mass of dispersed phase is what? Rho of oil into V of oil, right?
Okay.
Divided by total volume. That is 200 ml.
Okay.
Then rho of oil is 810 into volume of oil is 50 ml. So basically, so yeah, volume both are in ml, so it's fine. This is 200 ml. Okay.
Okay.
So what will be the answer? You can solve it.
Okay.
You didn't do like this.
Um, no, I didn't. I
What
mixed
you
it somewhere in that. I
what
don't know
you did?
actually. I'm not having that rough paper.
Okay. So it's come out to be
202.5.
uh, it's not matching with the right answer. Uh, oh, okay. This is
Yeah.
870. This is 870. Now I think it will match. 870 into 50 divided by 200.
Then also 217.5. But answer is in the range of 0.28, 0.3. But they ask a dispersed phase mass concentration.
No, I think I solved the wrong question. Yeah, 1 minute. You have asked me question number 8. This was like mass concentration.
Yeah, that yes.
Okay, so what I found is this was its density. Why I calculated this? Uh, I think this is question number 6. I solved question number
Hmm.
6.
Yes.
Oh, so anyway, uh, so it's correct. You are getting the correct answer for this because you are telling that it's
Yeah, it's in range of 215 to 220.
okay. So that's fine. So basically, dispersed phase mass concentration, it's already derived in the lecture. So that is mass concentration. It is dispersed phase bulk density. Basically, we want this divided by continuous
Okay.
phase bulk density. So that is correct, 217.5 divided by, you know what is
Okay.
continuous phase bulk density? So we need to calculate it.
Okay.
Divided by. So the same way that we have calculated it. So continuous phase. It's easy, right?
Yeah. That will be 750.
It is 1000 into 150 divided by 200.
Yeah, that will be 750. That's 150.
So what we get it?
0.29.
Correct.
Yeah, okay.
So what mistake you did?
I didn't calculate continuous phase bulk density. That's the problem.
Okay, fine.
Actually, in the lecture, that was directly told by the formula mass of dispersed phase to the mass of continuous phase.
Oh, okay. Yeah, you are. That's why
By that,
assignment is assignment.
yes.
Yeah,
Can you go through question number 16?
16. Okay, what is
Thermal
that?
response time.
Just a minute. Yeah, yes. In the yesterday lecture, I have discussed thermal response time. Like the recorded one,
Okay.
I have discussed the thermal response time.
Okay.
So basically, yeah, we need to calculate the thermal response time. So in this recorded session, I have discussed what is. So what's the doubt? Because thermal time is key, and this thermal response time I have calculated yesterday only, and this was found to be this.
Okay. Then I'll go through the lecture. I'll go through the lecture.
Yeah. Uh,
Question number 18.
18.
Actually, stop distance formula is initial velocity of particle into thermal response time, right?
What?
Stop distance.
Particle
Question
dropped
number
inside the
18.
warm stream, which is flowing at 10 centimeter per second. Initial temperature is this. We don't need to worry about temperature because we need to find the stop distance. So, uh, you know the particle response time, right?
Yes.
So it was already discussed in the lecture that particle response time multiplied by the velocity of the particle is the stop distance. So basically, if
Initially,
you
that's
solve
the formula. Initial velocity of particle.
what?
Initial velocity of particle into response time also gives stop distance, right?
Yeah, that's giving. What's the
By using that formula also we can calculate, but I didn't get the answer in a correct.
no? But you have solved question number 17.
18. Yeah, it's correct.
Okay, then basically I am talk. Can you switch on your camera because it will be good. I'm just talking like a.
Actually, the power is not in a good condition,
Okay, fine. Anyway,
so that's why I'm waiting.
okay. Which question? Which else question you wanted to ask? It's done. Assignment 1 done.
18 question. Yeah, assignment one only.
It's done, right?
Mm.
Now assignment 2.
No, assignment one only. Question number 18.
No, just discuss na question number 18.
Okay. Okay. Coming to
Where is your
assignment
mind?
2.
Is it fine? Anything you wanted to discuss in assignment 1? I'm okay with anything.
No, 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 no. Yeah, it's fine.
Okay. Now tell me. Assignment 2?
Can you explain about
What?
if we are having annual flow regime, slug flow regime, right?
Okay.
Can you see the third question?
Can you speak bit louder? I think, yeah, tell me.
Yeah, okay. I'll raise my voice.
Yeah.
Can you go to question number 3? There we are having annular flow
Which question?
regime.
Which
It was
question? 1
having
minute. Which question?
high gas flow and high liquid flow. Assignment 2,
Just
question number 3.
question number 3, assignment 2. 1 minute. It's from the
Yeah.
regime map.
Yes.
Okay.
Can you explain me once the concept?
Question number 2.
No, no,
Question
question
number
number 3.
3. Annular flow regime in a gas can be
Yeah.
observed at
Mm,
high gas flow and high liquid
yeah,
flow.
yeah.
So like if you see that regime map,
Yeah.
uh,
Mm,
so basically in regime map, we are having a mass flux of air,
okay.
and we are having mass flux of water.
Okay.
And then if you see that regime map, it's something like this. And then when both the things are high in this regime, this is
Okay.
the annular regime.
Okay.
So that's why we are saying that both should be high.
Okay. Coming to slug flow.
Slug flow. So in slug flow, it is
Yeah.
all the information I think is there in this map. Uh, it's the high, comparatively higher flow flux of water than the air in case of plug flow.
Okay. Okay.
Yeah, it is
Bubble flow.
there is this region, right? Slug flow.
Okay.
Bubble is like a very low amount
Slug
of
flow,
air
I
is there.
think both will have low gas flow.
What?
I think slug flow will have both low gas flow and low liquid flow.
In slug flow, it has a bit of high mass flux of water comparative to the air.
But in the question number 7, coming to vertical pipe, it was low gas flow and low liquid flow.
Slug flow, both, then it's the stratified flow. If both are low, then it should be stratified. Low gas flow and high liquid flow. High gas, it should be high. Uh, it should be high liquid flow and low gas flow. Then it's a slug.
Maybe I think you are telling for horizontal flow. Horizontal.
It's a
Coming
vertical.
to the vertical pipe,
Oh, okay. Sorry,
slug
sorry.
flow has
The,
low gas and low
yeah,
liquid
yeah.
flow.
Yeah, yeah. It's the vertical pipe. So it has different regime map. In first case, it's a horizontal pipe. Yeah. So that is the two different
Okay.
maps that are given there in the lecture itself. Okay.
In the lecture, I found that churn flow is heterogeneous flow.
Mm-hmm.
Bubble flow is also heterogeneous.
No, it's a question or you are asking what?
No, it's a question number 20. In the lecture, I found that there is a picture describing that churn flow is heterogeneous.
Question number 20.
Coming to the assignment answer, the answer was yeah, bubble flow.
I don't know why. Yeah, churn flow is also a heterogeneous flow. Why? I think you should.
Then why the answer was
I
only
think
bubble
you should
flow?
mail for this to which mail ID? I don't know. There will be a discussion group, right? Where you can ask.
Yeah.
So I think you can ask this directly there.
Yeah, okay.
All the TAs will be there.
Okay.
Anything else?
Assignment week 3. If I have, I'll.
What?
In 2 assignments, I cleared my doubts. I'm
Okay.
searching for third assignment if I have any.
Third assignment.
Yeah.
Okay. Tell me which question.
Can you wait for a second? It's loading.
Sure.
Mixture friction factor.
Mm-hmm.
8th question. Mixture friction factor.
Mixture friction factor.
Yeah. Actually, I got the Reynolds number, correct mixture Reynolds number. Whereas mixture friction factor can be calculated by laminar flow.
Mm-hmm.
That means 24 by RE comes 60 by RE comes according to the given question description.
Did you get
I
the answer?
couldn't get in the range of. I didn't get in the range of 10 square. It was in the power negative power.
Hello.
Yeah.
Yeah, you were telling about the mixture.
In order to calculate mixture friction factor was calculated by 16 by RE. Reynolds number of mixture will be taking. Whereas I got the Reynolds number in the laminar. So here I'll be using, in order to calculate mixture friction factor, I'll be using mixture Reynolds number, right?
Yeah, it should be mixture in all number, right?
Yeah, when I calculate that Reynolds number of mixture, 7.65 into 10 minus 3.
So, 7 points. What? What?
Sorry. Reynolds number I got 2090.306.
What is the mixture Reynolds number you are getting?
2090.306. 2090.306.
2090, correct? 2090. Hello.
I'm sorry, I lost my internet connectivity.
I'm unable to hear you. You may also type in the chat box. Hello.
Can you hear me?
I'm unable to hear you clearly.
Uh, can you see the chat?
Uh-huh. Did you send something?
Yes.
Where?
Are you audible?
Hello. Hello.
Hello. Can you hear me?
Yeah, now I'm able to hear you.
Okay, I got Reynolds number in that range. Whereas coming to mixture friction factor, we'll be using 16 by mixture Reynolds number, right?
I think it should be.
If we calculate it, the answer will be in the power of 7.65 into 10 power minus 3.
Mixture friction vector. Because
I
you
couldn't get
are
the answer in that range particularly.
not in the range of. You are getting 209. It's around. It's
Yeah,
crossing
Reynolds
the.
was in the range.
It's crossing the laminar flow regime, right?
Laminar flow regime actually 2100, it is less than 2100.
2100.
As far as discussed in the lecture. Yeah,
2100.
100. Yeah, it is actually less than 2100. So considering it is laminar flow,
What is the issue? Mm, Hello, Taruni.
tell me.
Yeah, have you tried this correlation? Like, what is the answer you are getting for when you are putting it in turbulent?
No, I'm not putting in turbulent. Actually, it was in the range laminar flow. How can I get it
No, no,
in
I know that.
turbulent?
Uh, I know that. That is in the laminar flow for sure. Mm,
Okay, I'll have it try. Wait a second.
uh, I actually I don't have the solution
Then
also.
I get in the range of 0.0. Answer will be then 0.011. Then also it is not in the range that was given by the answers.
0.011.
Yeah,
I
if I
now
use the turbulent.
now I understand what's the issue. 0.079. 1 minute. Let me check. 2092 to the power 0.25. 0.079. 0.079 divided by 6.7. 0.11. They actually, there was a mistake. The mistake is this, that first thing they have assumed it to be a turbulent flow. And second mistake is that it should be 10 to the power minus 2.
Yeah,
Then only you will get the correct option.
okay. Coming to the question
And
number
and
90.
you are getting your and if you are getting your answer wrong, I request you
Yeah,
to mail. I will also mail from my side. Okay.
okay.
Yeah.
Yeah, I'll mail.
Yeah. I will also mail.
Coming to question number 19.
19, because sometimes what happen, people also consider that anything above 2000 to be turbulent.
Yeah,
So
yes. But
may,
actually, I verified it in the lecture. It was
yeah,
clearly
yeah. So
mentioned.
according to lecture, it should be correct. Like it should be done correct. Like, but whatever the
Yeah.
like I will. Yeah. Which question you are saying?
Question number 19.
Fiji, you need to calculate.
Yeah,
It's
5G.
a Locard-Martini parameter, right?
Yes.
So
Whereas 5G square can be described as 1 plus C5 plus 5 square.
yeah,
But I didn't get the answer in the range of 180 and 230. They asked for 5G, relation is for 5G square. Can you verify it once?
yeah, 1 minute. 5G you are calculating, right? 1 plus C5 plus C5 square, right?
Yeah, 1 plus C5 plus 5 square.
Yeah, correct. That is correct. So it should be 1 plus C5 square.
Coming to C value is 20 because Reynolds number for both the
Yeah, that's
flows will
correct.
be turbulent.
That's correct.
So coming to 5, it is in the range of 40 to 50, so 46.51.
That is also correct.
Yeah, when we calculate 5 square will be 3094.
Okay. You need
Okay, they asked
they
for
are
5G.
5G. Yeah.
So square root of 3094 will be 55.623.
Mm-hmm.
But answer is in the range of 180 to 230.
I think yeah, just give me a minute.
Yeah.
I will try to see what's the issue. That is also slow. Okay. Yeah, it is opening. Like I'm trying to find out answer somewhere. Then we'll tell if they did.
Okay. It's okay, I can wait.
Yeah. Yeah, just a minute. Hello.
Yeah.
Sir. So I'm saying like I am unable to find the solution. So I'm trying to
Okay.
solve it for you. So let's see what will be. So C is 20, right? And
Yeah, C is 20.
5,
Pi
what you are
is
getting?
46.51.
Yeah, correct. That is correct. These two answers are matching also, right?
Yeah.
Into 20 plus 46.5 square. Let me calculate and see.
It will be 3094.38.
Into 20 plus 46.5 square. Yeah, 3093.25, right?
Yeah, they asked actually the equation is for 5G square. So
They
in the
ask.
assignment they asked for 5G.
So 5G should be root of it.
So square root of answer. That will be 55.
55.6.
Yeah, but
And
answer is in
what
the
is the
range of 180 to 230. They have accepted in the range of 180 to 230.
I don't know what they did because nowhere.
Yeah, that one is doubt for me.
Okay. Anything else? Like
Even
I will mail them.
uh,
Definitely will also mail them. But
yeah,
I
19
don't
and
know.
20 are interlinked.
Yeah, why there are a lot of mistake in the assignment solution.
Yeah,
I will check with them.
yeah, okay. That's all. Up to now, my doubts are clear.
Okay.
Thank you.
Anything else?
No,
Yeah. For regarding assignment 4, we discuss in the next class for sure. I will
yeah,
discuss all that. Whatever your doubt is. Okay. And I will
okay.
continue this discussion, whatever I'm doing. Uh, any suggestions on this session?
No, I think the session was good. Nothing much.
Okay, so do you want me to explain what I'm explaining like right from the start, or do you just want me to have a numericals?
I think explaining concept is good. It will be good if you explain some numericals also, because that
Yeah,
will help in lot in writing
that's
final
the way I'm
exams.
doing. Like Only the straightforward things I'm not doing, like all these are formula based things. But when you are studying
Yeah,
multiphase flow,
actually,
it is important to understand this concept of like from where the Navier-Stokes equation is coming and what are the different terms. So what are you currently
yes,
pursuing?
yeah, actually that was good. Knowing basics is also very good, but it will be helpful if problem solving session also conducted.
Yeah.
With problems,
What
it
are
will
you?
be good.
Okay. So what are you pursuing currently? Like BTech? You are in BTech?
Yeah, I'm BTech final year,
Okay. Which college?
JNTUK,
Which one?
Jawaharlal Nehru Technological University, Kakinada from Andhra Pradesh.
Okay. Okay. Nice. Okay. So okay. So you are planning to have a PhD and all?
No, actually, I'm doing honors course. There I have chosen this multi-phase flows. So I have to take the exam to get my certificate.
Okay. Okay. Yeah. But fundamentally, wherever you go, when you are studying multi-phase flow, you should know the fundamental transport phenomena like Navier-Stokes equation, derivation of that. What are the basic terms?
Yes, actually in our curriculum we have transport phenomena and fluid mechanics. So they helped us a lot. Actually, we completed both the subjects, so it is easier for me to understand for somewhat.
Yeah, yeah, that's true. And then you are following up this discussion. I don't know. I think in your UG, they have used BIRD, I guess.
Yeah, but that was a very famous textbook. We can
Yeah,
refer
but
easily.
I personally like real. If you want to go to advanced level, and whatever the derivation is based on it's not based on shell balance like not the usual things. So I don't know
Yeah,
if you are able to follow all these descriptions.
yeah. Currently, the main textbook will be good. References, they'll be given a lot of books. If we don't understand, we can follow any other books.
Okay. Okay. So my aim is to give some insight about this transport phenomena because many people don't know. Like few things that I
Yeah,
wanted to
actually,
discuss.
transport phenomena is main subject in order to understand the flows and
Yeah.
directions, how they will be acting.
Yeah. So that's why I'm not doing all these direct questions that are just based on the formulas. Formulas is there already in this. All the correlations were there.
Yeah,
Everything is there. So
yeah.
I don't find it too much of insight. So that's the only reason that I am not discussing. If I found something good, I discussed it like
If
in
we
the last.
discuss directly,
Yeah, yeah. Tell me.
yeah. If, if same thing was discussed, then the problem solving sessions will not be interested.
Yeah, because it's just the formula, just putting the formula and then solving it. So yeah, my
Yeah,
to have was have to give you a feel of fundamental transport phenomena that is used in multiphase flow, and then some of the numerical like the one of the recorded lecture that was uploaded yesterday. I have solved the thermal response time scale, and before that, in the before session, I gave you a brief like what is happening in the Stokes flow and what is Stokes flow. You may know by now because you did transport, but still, there were
yeah,
a lot of good discussion happened in the last session, and
yeah. I'll go through it. If any doubts, I'll contact you.
okay then just I think we'll wrap up if there is no doubt.
Yeah, yeah, sure, no doubts.
Okay. So it's
Thank,
fine. So it's fine not to have a lot of numericals based on direct uh, uh, formulas, right?
yeah, it's actually not a problem. Where we cannot solve, we'll be asking. If any doubts, yeah, there to solve.
Okay. So yeah, that's what I am asking. Like, what you really want in the discussion are like mm, the concepts or the
Basically,
numericals.
I am. I'm thinking for questions what I'm not solving and why I'm not solving. That are the
Okay.
reasons in order to join the session today. As I got cleared, I'll mail them.
Okay. For now, everything is cleared for till today, right?
Yeah, today till clear.
So it's helpful, right? Hello?
Yeah, yeah.
Okay, then fine. We'll discuss it like this only. We are remaining 4 sessions to discuss any other doubts that you have, and just come. We'll discuss it.
Yeah, sure.
Okay.
Thank you so much.
Thank you. Bye.
Bye bye. Have a good day.
Same to you.